All right, so here we are starting class 25. We make it to 30 by the end of the semester, so yeah, it's going well. We're going to start doing a little bit more WMS today, getting into some actual like flow prediction rather than just delineating watersheds and stuff like that. We're going to get into the nuts and bolts of predicting the runoff. We're going to do that according to 3 methods, and I've given you a handout here. Everybody's got a copy of the handout. There are 3 activities, one for each of the methods that I'm going to show you today. And with each of those activities, my thinking is that you'll get a little bit more practice with the basics, starting from scratch or pretty close to scratch, identifying a project area, getting the necessary DEM data, and then delineating the watershed. And then once you have the watershed characteristics, like its area, its slope, and some other information related to time of concentration, then we're going to calculate the runoff. The real sophisticated stuff begins on Thursday. On Thursday, we're going to move beyond just estimates of runoff, and we're actually going to use WMS to calculate curve number. And so it's going to be going in and getting that soil type data and the land use data that really turns something that's kind of an art at this point into a reproducible science that's a lot more defensible if you had to explain a model and why certain assumptions were the way they were. So today, these are important models. A lot of people use the rational method and national streamflow statistics and TR55. It's not like this is nonsense that doesn't get used. I mean, there are people all over the country that are using these methods for design, but the real in-depth power stuff begins on Thursday. All right, so let me give you a little bit. You already know all about the rational method, and we've talked a lot about that. Just a bit of background on the second of the methods that we're going to use, the national streamflow statistics. The USGS, which is a division of the Department of Agriculture, puts together a study for each state in which they have done a statistical analysis of rainfall patterns and stream flow. And so they have equations, and you can just put in some very simple characteristics of the basin, and it'll predict what's the 10-year runoff or the 25-year runoff or so on. In West Virginia, the equations are based on the watershed area. There are some other places, like out west. I was just looking at some regression equations for Arizona. And in Arizona, those regression equations take into account the basin area, but also the elevation that you're at, and then the precipitation of a certain size storm. So like, for instance, the 5-year storm, they want to know at that location what's the typical rainfall like, and then they'll generate the runoff coefficients. But we'll get a chance to see what the equations look like within West Virginia. There are a couple of different regions within the state, and those regions are defined broadly by the geography of the state, where we know that there are certain locations that are more mountainous and certain spots that are more plateau-like in topography. And it's also based on the study of all of the rain gauges and stream gauges that are in active use or have been in historical use in the past. Because there are plenty of places where they used to gather hydrology data, and then due to budget cuts, those gauges were eliminated. And so here's just a scattershot look at where all of the gauges are across the state. And then these are the 3 divisions that the USGS has carved up West Virginia into: the Eastern Panhandle, the Central Mountains, and the Western Plateau. So here in Cabell County and all the way out towards Clay County, we're considered the Western Plateau region. All right, so here's what we're going to do. Let's just, because we didn't do this together live for day 1 of WMS, let's work through the beginning stages of activity 1 together, just to make sure we're all on the same page. And then I'm going to turn you loose when we get to the point where you need to start working through these bullet points on activity 1. All right, so the first step is to start WMS if you haven't already. Now, if you get an error message about licensing, let me know, because they've issued some new serial numbers and I can give you one of the updated license codes if the old one that you've used previously isn't working any longer. All right, so start the program, and this wizard hat on a roller skate, or whatever this is supposed to be, the hydrologic modeling wizard, is where I always start. And the reason I always start there is because it reminds me that I need to begin a project name. And so browse to a location that you're going to be able to find again. And save, and then you're going to have to click Save again here, because it doesn't actually create that project file until you click Save underneath the Browse for File Names. You click that, and now finally you're establishing the WMS file. Now let me mention something here. This extension .wms, that includes most of the features that you'll establish and create for a watershed model, but there will be other files in addition to this one that get downloaded and accessed in this whatever directory you've specified. So, when we're done with this activity, you'll notice that there are several different files in that folder. And when you're done modeling, the WMS is the only one that you need. There are going to be some elevation data project files that you can delete if you're trying to save space, but I usually just leave them there in case I wanted to come back and load the DEM again another time. So did everybody get a file name? Everybody have the program running? Any technical issues this morning? Everybody good? All right, so we'll click Next. And now, oddly enough, in the most recent version of WMS, I'm finding that the project projection and project boundary tool isn't working as well as it used to. So hopefully we'll be able to find the location. Zone 17 is what you need to specify for the projection, UTM Zone 17. If you haven't already done that from a previous activity, go into Define, and then Global Projection, Set Projection, and UTM Zone 17 is, we're in the northern hemisphere, and the project is between 78 west and 84 west. If you look at the handout, it says that our longitude is 82 degrees 14 minutes 46 seconds west. So that puts us in Zone 17. All of West Virginia is in Zone 17. Okay. So click OK, and now for the project boundary, once you click Define, it's going to bring up this little tool for the virtual map locator. And here's the odd thing is, it didn't used to ever say, sorry, we have no imagery. Now I can get around it for me if I jump to a location, toggle back and forth between satellite and map. Now finally I'm in the ocean off the coast of Greenland, and I just browse over. There we go. It's probably because it's got this latitude and longitude wrong. But if you browse towards between Charleston and Huntington, we're zooming in on Ona. Here's Blue Sulphur Road, zooming in a little more. Here's Lycans Branch. So this is about the region that we want to be on. Okay, so I'll leave that up, circulate around, see how it's going with browsing to your project area. If it's you can use the satellite if you like, but I prefer the map rather than the satellite because it's got the road names and it's just a little bit less busy. Oh, sorry. All right, so this dude jumped to toggle that back and forth. Okay, well, put in like 38 and 82, yeah. Well, that's odd that it's, yeah, we'll try closing that and then go back to it and, yeah, define again. It's not giving you the mapping tools. Okay. Okay, oops. All right. So here is, now you'll notice that when you have a location specified, what it's using is these edges of however far zoomed in you are. That's going to be the project window that it's working in. And so if I zoom way out like this, it's going to take forever to download all that elevation data because it's such a wide view. So as much as possible, you want to zoom in on the project area that's actually, where you're working. But then you don't want to go zoomed in too far because then the watershed may go off the window that you're actually looking in, and then you have to download it all from scratch again. And so it's kind of sometimes a little bit of an iterative process, making sure that you get all the DEM data that you need. Okay, so when you click OK, you'll notice it's filled in the X and Y coordinates of the edges. And click Next here. Web services means that it's going to automatically download the DEM. So click Next. And then if you scroll over, all we need right now is the United States elevation data 10-meter resolution. We don't need any of these other options. And click Download Data from Web once you've got it set to United States elevation data. I'll take a moment to go and get that. Now here it's prompting you to specify the resolution, and sometimes, even though this is a 10-meter resolution DEM, sometimes it would maybe say 12 or 11.38429. And it's basically suggesting that it could downsample and smooth the data if it was going to be a big file. And you can always override that and just say, no, it's a 10-meter DEM and I want the original 10-meter resolution by just typing in 10. But that's sort of why it's prompting this window right now, is in case you did have one of those really wide views, it's a way of thinning out the data so that it loads faster and doesn't take up so much space when you save the file. All right, so you'll notice in the background now I've got my contour lines, and the next step with Topaz is that analysis of where the streams are going to accumulate. And it does that just by looking for each cell, whether the adjacent cells are higher in elevation or lower in elevation. And so it kind of, for each one of those analyses, each pixel on a pixel by pixel basis figures out whether, if a stream drop fell on it, what direction that stream would drop, the water would go based on the elevation of the adjacent cells. So click Topaz now here. Miranda, I think that the issue that you had when you were working through that first activity was the display threshold for where the streams are. So let me show you, once we compute, I've set it to 15 acres right now. And so now you'll notice here is some streams. Now look what happens if I change the display from 15 acres to 200 acres. Okay, see where all these blue streams are? Each one, blue means that there's at least 15 acres of area upstream contributing to that. But now if I change it to 200 acres for display, the length of those blue lines is going to decrease. And so it looks like the stream isn't there. And in some cases, if you had the upstream area set to something really high, like 2,000 acres, it would look like there's no streams anywhere. But it's just that in this region, there are no watersheds with an area of 2,000 acres. And so you kind of sometimes have to fine-tune what you use as the minimum upstream accumulation of area for display. Okay. Well, it's a mystery then. Maybe your computer's haunted. All right, so be sure to save occasionally, because this program, as nice as it is, it sometimes crashes. And it was originally developed by students, believe it or not. They did the programming for it, and it was just spun off as a commercial enterprise. I don't know, it's been maybe 10 years ago, but for a long time it was a university-run and supported software program. All right, so the area that we are interested in is, let's see, we place the outlet and delineate the watershed. I want to make sure, now I know that this is the branch that I'm interested in, but if I didn't know, what I'd do is throw a map in the background. And so I can get online map and world street map. So here this plus get online map, bring up the world street map, and it'll take a minute here. You can see it's streaming a map into the background, and then I'll be able to ensure, see Likens Branch, it gives me the name of the road there, Likens Branch. Here's Little Cabell Creek. We want Likens Branch before going under Blue Sulphur. Okay, yeah, this is Blue Sulphur here. All right, so the location that we're going to drop the outlet, if we go back here into the Hydrologic Modeling Wizard, for choose outlet location, we're going to create an outlet point, and then the place you're going to drop it is just before Likens Branch goes into that stream that runs along Blue Sulphur Road. So you drop the outlet just before it joins, and then delineate watershed. All right. So what I'm going to do now is I'm going to stop talking and give you a chance to work independently through each of these bullet points. Once you've made some steady progress on that, then I'll also work through those steps in the screen recording, just so that if you need to come back later, then that'll be available to you. Okay, so starting with a delineated watershed where we've got the area, we've got the outlet specified, but we haven't done any modeling yet. I'm going to go in here to the Hydrologic Modeling module, and instead of HEC1, I'm going to have it do the rational method. And if I want to bring up the windows of the rational method, I'm going to select the basin and double click. Okay, the runoff coefficient for this 0.6, let's assume. And for the computing the time of concentration, I'm going to change it to the lag time method of the SCS. Now, it doesn't know the curve number, so I have to manually put that in. Let's say that we know a typical value in that area is about 75. So you'll see here that it's calculated 25 minutes based on the slope, based on the length of the watershed, and the curve number that I just specified. For the rainfall intensity, it's going to Hydro 35 based on the latitude and longitude, so it's kind of nice that it automatically, if you say get online data, it goes to the national, or the precipitation data frequency server, and you click on whichever year you want to use. And so I'm going to do the 10-year storm. And for our time of concentration, it says it's 26 minutes. So it should be between the 15-minute depth and the 30-minute depth. So it's going to be maybe 3.5 inches approximately. So when I click OK, it's using 3.2. It interpolated the rainfall depth that's needed. And here you can see the flow rate, 312. How many of you got a flow rate that's in the neighborhood of about 312 for the overall watershed? Did I say 300? 512, yeah, 512. How much? 490? So any difference is most likely just where you place the outlet. If it's further up that stream, then your contributing area is going to be less. All right, so compute hydrographs, click that button, and then it'll just make a graphical representation of that peak. It's not a lot to look at for a rational method. It just assumes a triangular hydrograph. But there it is, we've got that triangular hydrograph. Some of you, I think, weren't seeing it initially because you weren't in the hydrologic modeling module. If you're in any of the other modules, then you don't see the runoff hydrographs. But if you go to the hydrologic modeling module, then you do. Now, you could make changes to your basin and see what that does to the hydrograph. So for instance, if I said, let's make the time of concentration be 20 minutes, then I'm going to compute a new intensity based on 20 minutes and then compute a new hydrograph. Then we can look at that comparison. So now you'll see there's two different hydrographs. The yellow dotted line was when I had the original time of concentration and the original rainfall intensity, but then if I have a shorter time of concentration and a higher intensity, then that's what the peak hydrograph looks like for the new conditions. So you can, if you want to get rid of a hydrograph, then you can delete all if you want to start from scratch, and then calculate your hydrographs another time. So it'll just keep layering them on top of each other until you go and either delete previous or delete all for the hydrographs. All right, so then the next step is to break the watershed up into 3 parts. And so we're going to be dropping outlets. Now you can put in the outlets either through this wizard, or you can just do it within the tools. And I'm going to do it rather than using the wizard. I'm just going to use these tools that's in the drainage module. So while in the drainage module, I'm going to zoom in on the place that I want to put those. So drainage module, here is the create outlet point, and I'm going to drop one of them here and one of them there. And then DEM, Delineate Basins Wizard, gives me this warning that all the previous basins are going to be deleted if I delineate again, and click OK. All right. And there they are, the 3 basins that I want to take a look at for the next part. All right, so if you've got these 3 basins, then what you can do is assign different characteristics to each of them. Like if you knew that one of them was mostly a developed area and one of them was less developed, they could each have their own C value. And so what I was saying on the handout is this upper left basin, what if we had a C value there of 0.4, let's see here, number lock, runoff coefficient of 0.4, and then the time of concentration we compute from basin data. We do a lag time with a curve number of 70. We get the time of concentration from that. We can compute the rainfall. Okay. And then let's just do all of the basins there, except for I don't know which is which. So maybe I'll do them one at a time. The upper right, I guess I better look and see. That was 5B is the upper right. Okay, so the upper right runoff coefficient was 0.55. The time of concentration, we're using a curve number of 75. And then the computed intensity, it's just going to get off the 10-year. And the lower basin is a little more developed, so we have a higher C value. We need to do the time of concentration. All right, we can compute hydrographs for all of them. And you can see here we've got 140. Here we've got 218. Here we've got 210. So did everybody get hydrographs for each of the 3 subbasins? File. So the file in question you can get through MU Online. WMS files is the folder. Then download that GDM file to a spot that you'll be able to find it again. Okay, does everybody have 4-hurricane-dem file.gdm? Everybody's got that? Okay, open it with WMS, and it's a trimmed DEM file. It's a DEM file that I previously downloaded from the USGS and then trimmed it and then saved it in the WMS specific DEM format. So that's why it's this odd shape, is I trimmed it to only include the areas that are relevant. So we will load it, run Topaz, and so you can get to Topaz either through the Hydrologic modeling wizard, or if you go to the drainage module, DEM, compute flow direction / accumulation, there's Topaz. And so I'm going to click run Topaz, so OK, and it'll take a while to do this. Beginning, normal program termination. Oh, only took 1 second. I suppose some of your computers may take a little bit longer than that. But now those blue lines go in there to represent any location where there's a lot of contributing area upstream. And if you want to adjust, then you go here to Display Options, DEM Data, and that's where you can adjust whether it's 15 acres or 50 acres. You know, how much upstream area is actually enough for it to begin to put the blue line there. And then we want to delineate just at some point in the far western outlet. Now, don't do it in the wrong spot. Don't choose one of these extraneous streams. You want the main stem. And so, you know, here's the main stem, and so let's drop a outlet towards the far western edge of that. And then you can go and DEM, delineate basins wizard, OK, and it delineates. This is going to take a little while because it's so big. It should be slightly more than 50,000 acres once it finishes all its calculations. You can also do that through the wizard. All right, 51,000 acres is what mine is, depending on where I clicked on that stream. So now that we've got the watershed delineated, we're instead of switch to the hydrologic modeling module, and instead of doing rational, this time we're going to do NSS. And so I'd like you to try and work through the bullet points that are on that handout for the NSS method. And of course, the way that you bring up the dialog is to select basin, double-click on the basin, and then it'll bring up the dialog box for the national Streamflow statistics. And hint, we're not in Alabama. West Virginia, peak flow, western plateaus. We are in max flood region 4. And then compute results. So there's the max flood envelope. Here is the return period versus the peak. I want to export that. Call this one hurricane. hurricane, yes, okay. Alright. I could put that. There it is. Open it up. And then I can make an XY chart. Let's put in the chart here. Yes. And we will select data here. The X values. On the X value, I want to have the return period. For the Y values, and have the peak flow. Now, I can't have it include the 0 if I want to do the log. I'm going to have to take that. Hold on a second. Take that down. I'll select data. Delete these lines because they're stupid. Put in some axis titles. This is the return period. And here is the peak flow rate.
So it's too high.
Okay, I'm going to make this logarithmic. Oh, that looks nice. All right, so the NSS says that the 500-year storm is going to be 14,000 CFS. But if you look at this estimate of the max flood envelope, what is it saying the max flood envelope is? It's saying 78,000. So that is way, way out there. I mean, that's like maybe the 100,000-year storm, or maybe like the storm that killed the dinosaurs, if there was a storm that killed the dinosaurs. I guess it was a meteor or something. But I mean, it's interesting. That's really, really way out there compared to what we see for the return periods. And if you put it on a logarithmic scale, then it turns out to be fairly linear. And so we could, if we wanted to insert an equation there, we could see like what's the equivalent return period that's assumed by the flood envelope of 78,000 CFS. All right, well, we've only got 4 minutes, and I don't think that's enough time for us to do activity 3. So that's where we're going to pick up when we meet on Thursday. We're going to start with this TR55 stuff on Thursday. So now everybody has WMS running. My suggestion is work through these 2 activities again. They should take you 5 minutes once you're familiar with the program and once it's not giving you error messages and stuff. Each one of them, you should be able to identify an outlet, download the data, delineate the watershed, come up with a peak flow rate literally within about 5 minutes. And so practice, take a stopwatch, you know, like it could be a Rocky montage, run up the steps of the library, then delineate the watershed again, that sort of thing. And yeah, get hard on how doing this stuff. And then we'll get together on Thursday and do TR55, and then the beginning part of calculating curve numbers using the underlying GIS data. So you do have a homework assignment, and Thursday, let me remind myself what's on that assignment. We may need to push back the deadline depending on what questions I ask you on that assignment. I don't remember exactly. So let's pull it up. Homework 10. no, you can do this by Thursday. It's basically just delineating the watershed. That's not beyond your ability at this point. I was worried that it was going to have some TR55 stuff on it, and it doesn't. So the homework's due as scheduled, due in class, at the beginning of class on Thursday, and then we'll get into some more advanced, deeper stuff in class on Thursday. So bring your computers again on Thursday. See you then.